and welcome to your Engineering Tomorrow Embedded Systems Lab intro. My name is James Venditto. I'm a PhD student in electrical engineering at Columbia University and a graduate of the University of Notre Dame, where I did my undergrad, also in electrical engineering, with a concentration in semiconductors and nanotechnology. So as an engineer, I was especially interested, and still am, in optoelectronics and photonic devices, which are a type of semiconductor device where either light produces electricity or electricity produces light. Think things like lasers, photodiodes, and LEDs, which we're going to see later in this lab. Particularly, I eventually want to use these devices to address issues like renewable energy. Think solar energy or energy-efficient lighting, or sensors in cities, like detecting air pollution or gas leaks at their source. As for why I became an engineer, I was attracted to engineering from a young age, not just because I liked math and science, although I did, but because I wanted to solve real problems that affected real people. In high school, I found myself interested in a little bit of chemistry and a little bit of physics. So I kind of thought to myself, how would I use that to, do something interesting and relevant that I can feel proud of? I decided, let me look into what these majors study in college and then what kind of jobs there are out there. And I eventually stumbled upon electrical engineering, and I realized that it's actually really, really broad. Electrical engineers do everything from the power grid to renewable energy to lasers and all kinds of things in between, including embedded systems that we're talking about today. So by studying electrical engineering, I didn't have to have my whole life figured out at 18 years old. I could take different classes and kind of figure out what I really was interested in along the way. And so for me as a high school student, that was really comforting, that I didn't have to have everything figured out at 18 years old. And that eventually led me to semiconductors and deciding to get a PhD because I wanted to keep learning more and getting a little bit more specialized. So that's really my path towards my career. Now, something interesting that I'm really proud of, though, actually was an embedded systems project. Even though I'm a semiconductors person, I actually have a bit of a background with this. When I was an undergrad, I did something called an REU, a research experience for undergraduates at New York University. During that project, I worked with a lab called Sounds of New York City, or SONIC, and they've been working on monitoring sound pollution here in New York City at a local level for several years. Now, why that's really important is traffic issues, and that's things like construction noise, loud music, other, just kind of loud sounds in your neighborhood that might wake you up at 2 a.m. that are technically illegal. They vary from street to street, right? This is an issue that cities, try to solve to improve the quality of life for their residents and, in fact, their health. But, you can't be on every block and know what the problems are locally. So what they designed in this lab was actually something, a type of embedded system where we had sound sensors, basically microphones, attached to these tiny little computers called Raspberry Pis. And they collected data of when, where, and how loud unwanted or illegal noise was. This information can then be given to the city so that they can send noise inspectors to places that really need it. When I joined the group, they were looking to expand into monitoring air pollution. So, in the last few years, we've had some issues with wildfire smoke, not just from areas with wildfires, but even going to cities like New York that are far away from these fires. And that really affecting the quality of life here. And so monitoring air pollution locally is really important for understanding, health issues that might affect people in their neighborhood. So what I worked on was adding a air pollution monitoring sensor to these Raspberry Pis. And what did I do? Along the way, I wrote some code, I wired up some circuits, and I analyzed data to report trends. In the end of the day, I really enjoyed this project because it combined a lot of the things I was learning in school with stuff that I think you can see really affected my community. And I feel like made a positive impact on the city that I'm from. And I'm pretty excited about where it's leading. It's an ongoing project. So I contributed to something bigger than myself. And that was really a formative experience for me. So hopefully that gave you a little flavor of what, one type of embedded system looks like, right? Monitoring pollution in the environment. But at this point, you're still probably thinking, okay, that's nice, but you keep throwing these words around. Embedded systems. James, what are you talking about? What is an embedded system? First, I'm actually going to answer that question. And then we're going to get into the nuts and bolts of those embedded systems, basic electric circuits, and a little bit talking about coding. Then I'm going to introduce the lab activity, where you are going to be designing a traffic light, which is one of the simplest but most important embedded systems out in our world. Though before we get to that, though, I do want to acknowledge our breakout development team. As always, all ET labs are created by a team of professional engineers and engineering students. In particular, I want to draw your attention to the mixed educational backgrounds of our team. We have electrical engineers, computer engineers, mechanical engineers. Engineering is a team sport. I'm going to emphasize this several times, but I want to kind of drill that into your head. This lab in particular has had multiple iterations that were worked on by different teams in different times, and that illustrates the concept of iteration. Kind of like I just talked about with my project, how I was only part of it for a short period of time, but different teams build up their work over time. And we do something called iterating, which is improving our design to make it work even better. We learn from our mistakes. We learn from, our previous development cycles. We don't just make a product and go let's home, okay, we're done. We look back, we're like, okay, we made a great product, but how can we make it even better? And sometimes you bring in new people with diverse opinions to help you see things you didn't before. So that's why it's important that you work with a big team, and I'm going to emphasize this several more times. So finally, what is an embedded system? Simply put, an embedded system is a combination of hardware, or circuitry, and software, or code, that interacts with the world around it to do something useful. Importantly, there needs to be some sort of intelligence, basically a computer of some sort, where we can actually write the code into, right? You have to put the code somewhere. Because that intelligence is embedded into the world, or sometimes within an even larger device, we call it an embedded system. Let's do a quick exercise. Can you name any examples that fit this definition? I'll give you a hint. You may have one in your pocket right now. Here are a few more examples. As you can see, they come in all shapes and sizes. Some are complex, some are very simple and only perform one task. Some are kind of standalone, and some are part of a larger system. All of them, however, are embedded systems because they combine code and circuitry. Now, what kind of engineers actually work on these might be your next question. I want you to think back to what I just said regarding engineering. Do you remember? I said that engineering is a team sport. And living in an increasingly digital world, all kinds of engineers interact with embedded systems, particularly through sensors. However, there are, yes, certain types of engineers who specialize in developing embedded systems because they have expertise with circuits or code or a combination of them. Continuing our line of thought, though, I hope you're getting a sense of how these systems are incredibly useful and how they can play a key role in solving the pressing issues of our time, which you can see here. That can be things like monitoring the power grid, security, looking out for pollution. Maybe one of you guys will develop the next great embedded system that solves one of these crises. Before, though, you get to saving the world, I do need to make sure you know all the basics. So here's how this presentation is going to work. I'm going to start by walking you through the basic circuit components, and then introduce several practice circuits so you can get a feel for how everything comes together. This is the hardware part of embedded systems, the physical components that do things in the real world that we can see. Next, I'll tell you a bit about programming, which is the software side, where logic gets embedded into that hardware, giving a form of intelligence that allows it to act dynamically with respect to its environment. Lastly, I'll give you that traffic light mission I discussed, where you'll get to put everything you've learned into practice. Along the way, you'll get an impression of what kinds of things electrical engineers and computer scientists do in their daily lives. Let's now get into the building blocks of those systems, the circuits, the hardware. This is also a good place to remind you that all the information I'm sharing today is also in your student interactive workbook. So if anything is not fully clear, know that there are additional slides and activities to help you practice your understanding further. And since this is a recording, please feel free to come back to any parts of the presentation that you might need a refresher on. Before we discuss what a circuit is, let's talk about electricity itself. If you recall from chemistry class, every atom has electrons, which are tiny subatomic particles that carry an electric charge. And conductors like metals, they can move when we provide a push. And we'll talk a little bit about what that push is later. And when a bunch of electrons flow at once, they'll carry that energy along a given path. This flow of charge is what we call current. At at its heart, a circuit is simply a complete path for current to flow. When we design a circuit, we're creating a path to deliver the energy supplied by something like a battery or the power grid to a device where that energy can be useful, like a light bulb or a motor. The current and the electrons that it's made out of are simply the delivery mechanism for that energy. They're not the energy itself, they're simply delivering the energy. Think about it like a conveyor belt. The belt itself is the flowing electrons traveling in a complete path in a loop, kind of circulating around. The boxes like on the belt that are moving, they're the energy that you're delivering. It goes from like one end and it gets to the end of the belt and then it's like taken off the belt. That, box is delivered, the energy is delivered. But the belt loops back around and then more boxes are placed on it at the other end. That kind of continuous flow is what's actually, happening with the current. Again, the electrons are simply delivering the energy. This is also why you need a complete path back to the battery, because they need to make that loop. The conveyor belt needs to loop back around. To make these points clearer, I'm now going to switch over to a demo circuit that will help you visualize what I said just a bit better. Welcome to your very first circuit demo. I'm going to construct a simple circuit and walk you through a couple of the things that you can expect to see in circuits, and then we're going to talk about our observations from this. So I'm going to start by putting a battery down. We need some kind of energy source for our circuit, and the battery is going to be the one in this case. You can see these little blue circles here. These are the electrons, and right now they're not moving. We're going to make them move once we have a complete loop for them to travel in. Next, we need some wires because we need to connect everything together. And then we need something that's going to do something useful or interesting. In this case, a light bulb that will light up. Then we need to connect everything together. So we're going to make sure they're all connected. And voila. Now my circuit's complete. There's a complete path for the electrons to move, and there's an energy source for them. So you can see them traveling along, and the light bulb is emitting light. This is a complete circuit. Now, if I were to remove one of these circuit elements, I broke the circuit, and now nothing is happening. There's no charge moving. So that's an important observation. If there is not a complete path for the electrons to flow, even if there is an energy source, nothing is going to happen. Let me put a switch in so that I can continuously turn it on and off again. Like how a light switch at your house works, we can open and close the circuit so the light bulb goes on and off. This is exactly how a light switch in your house works. The next thing I'm going to do is change the light bulb itself. So I click on the light bulb and you notice something here says resistance. And there's this thing called ohms. We'll talk a little bit about what that is in a minute. But let's observe if I change the slider up, I increase the resistance. Notice what's happening. The electrons are slowing down. They're slowing to a crawl now. And the light bulb isn't emitting very much light. So this is perhaps an extreme example. A little bit lowered it a little bit. They're a little bit faster, but it's still not as much light as we saw before. So increasing the resistance is slowing down my electrons, and it's decreasing the amount of light I have. Now, as I keep going in the other direction, you'll notice as resistance gets smaller and smaller and smaller, the electrons are speeding up and the light bulb is getting brighter. That means that more energy is being delivered to this light bulb, and something is causing the electrons to travel faster. Now, if I keep doing this, at a certain point, it might seem like a good idea to keep lowering this resistance, whatever it is, more and more, right? Brighter light bulb, that's good. Except, what just happened? The battery is on fire. The electrons seem to be going 1,000,000 miles an hour. Maybe my light bulb's really bright, but my battery's on fire. That can't be a good thing. It says speed limit reached, current animation speed. Something is weird in my circuit. And then if I push it all the way to 0 ohms of resistance, the light bulb's not even glowing anymore. So what happened here? We're going to talk about this, but as you can imagine, this is not something that you want to actually have happen in your circuit. So now the last thing I'm just going to point out is that if I were to remove the battery and then close the circuit and connect everything, nothing is going to happen. I just want to make this clear. If there's no energy source in our circuit, nothing can happen, even if it is a complete loop. And now I'm going to return to the presentation and we're going to talk about what some of this means in more detail. Now that we're back, let's talk about some of our observations from that demo. We saw that when the switch opened, charge stopped flowing around the loop, even when the battery was still connected. When it was closed, charge moved again. We've already heard the term current before as the word that describes the flow of charge. And now here we see it's an actual quantity that you can measure. The unit for current is the amp, and we often use a capital I as the shorthand for the word current. The larger the number of amps, the greater that flow of charge is. I'm going to use an analogy here to the flow of water in a pipe to try and make some of these concepts a bit clearer. And you might, also connect that with the animation we just saw. Think of current as the flow of water. The faster the water, or the faster those electrons are moving, the greater the current. We can measure the flow rate of water, or in the case of electric current, we can measure the number of amps. For those situations where we saw the electrons moving quicker, those circuits had a larger number of amps flowing through them. Now, what about the battery? We saw that the battery somehow provided a force or energy to get the charge moving. When we removed the battery from the circuit, even when it was a complete loop, nothing happened. This notion of energy or force is something that we call voltage. By definition, voltage describes the potential energy per unit of charge. Effectively, how much energy each of those individual electrons has been given to travel in a full loop around the circuit. Now, that might be kind of a weird concept to get your head around. So it's okay to simply think of voltage as the energy needed for current to flow, or a force that electrons feel. As we saw before, current will not flow without the battery. So we also need a voltage drop to kickstart everything. Voltage is measured in volts and is also shorthanded by the letter V. So that's pretty easy to remember, at least. Now, coming back to my water analogy, you can think of voltage as like tilting the pipe, giving it a bit, putting some gravity in there to actually get everything to start flowing. If you just laid the pipes out flat and filled them with water, the water wouldn't move. It would just kind of sit there. But if you tilt a pipe like this, the water will now flow, kind of like flowing downhill on a mountain. Putting a battery or a voltage into a circuit is the exact same thing. I'm giving it some kind of kickstart to get it to start moving in the first place. Lastly, we tinkered with that light bulb and we saw that thing called resistance. And now we're going to talk about what that term is. Now, some of you might think this is pretty self-explanatory, and it is. Let's see if we can use those concepts to actually intuit what's going on here. Remember when we raised the resistance of the light bulb? So first I raised the resistance. The light bulb got dimmer and the charge slowed down. Those electrons started moving slower and slower. Now what we can say is that as resistance increased, the current was decreasing, right? Because the electrons were traveling slower. When I did the other way, I lowered the resistance, the light bulb got brighter and brighter, and those electrons sped up more and more. So now we can say that as resistance decreased, the current increased. Therefore, we define resistance as the difficulty that current has flowing. Resistance is measured in a unit called ohms, usually represented by this funny looking symbol, which is the Greek letter omega. The shorthand for this term resistance is just the letter R, another very creative but easy to remember shorthand. To conclude our water pipe analogy now, resistance is like narrowing the pipe, limiting the amount of water that can pass through. So as the name suggests, resistance tells us how much a device resists charge traveling through it. The larger the resistance, the harder it is for charge to travel, which means you need a larger voltage or a larger force to obtain the same amount of current. This relationship can be summarized in something called Ohm's law. Current equals voltage divided by resistance, which is a foundational law of electrical engineering. This is like Newton's laws, but for electric circuits. Using this law, we can describe many other key phenomena in circuit design. Now, kind of presenting it that way, you might be thinking that resistance, is a bad thing, right? Because we're limiting current and we want more current so we can deliver more energy and get brighter light bulbs and things like that. Now, that's true. Sometimes resistance is a bad thing that we want to avoid, but it can actually also be something useful. Think back to the problem of our battery burning out. So now we're going to finally answer that last question, that quite literally burning question. Let's use our new concepts to try to figure out what went wrong and how resistance might actually be our friend here. Again, according to Ohm's law, current is voltage divided by resistance. Consider the situation we had before. The voltage value is constant. We had a 9-volt battery there, and it was 9 volts the whole time. The battery did not change. The only thing we changed was the resistance of that light bulb. As we make R smaller and smaller, we're dividing by a smaller and smaller number, and the current is getting larger and larger. This eventually becomes a problem because most devices are designed to handle only a certain amount of current. You can think about it, right? If the current is delivering energy, the higher current, you're starting to deliver infinite energy. And well, you can't do that. So something is going to break, right? We actually have a term for this condition of dangerously high current. That is called a short circuit, which you may have heard of before. A short circuit occurs when current has a very, very low resistance path. Like resistance is almost zero, very, very close to zero at least. And that results in the current becoming excessively large. Short circuits are usually unintentional. You don't want to destroy your equipment, but they can damage your devices. And in worst cases, as we kind of saw with the little fire picture there, they can actually cause devices to catch fire. And so this is the cause of most electrical fires. So that's something we obviously want to avoid. Our circuit simulator is a safe environment, but we don't want our devices to break even if they're in the virtual world. So we are going to want to avoid these in the circuits that we construct. So since the problem is too little resistance, the solution is quite obvious: to add a little bit more resistance. So resistance actually wound up being our friend. It's how we prevent short circuits. Now, your next question might be, all right, how do I actually put resistance in a circuit? Like, what do I do? And luckily, we have a device that takes care of this problem. It's called, very creatively, a resistor. And it is simply a piece of material engineered to have a very specific resistance value, say 100 ohms. This little guy has exactly 100 ohms, and you can put it in your circuit. There's a lot of ways that we can make them. There's different materials we can use, but most modern resistors, like the one that you see in this picture and that you'll see in your lab activity, are made from special blocks of carbon, actually pretty much the same material that's in the tip of a pencil. It allows electricity to flow, but not super well, and you can do little different things to it to change the exact value of the resistance. The colorful stripes you see on it are actually a universal code that tells the engineers what that resistance value is. And so back to our water analogy one last time, what this is like is if we deliberately narrowed the pipe to keep the flow of water from getting out of control. Like we want to very tightly regulate how much water is flowing because we don't want to swamp everything downstream. Now that we've identified the resistor as the first key component we can use to build circuits, we're going to take a look at a couple of others. We only need a few more to actually construct a real embedded system. By this point, you also may have noticed that you don't have any circuit components in front of you. That's because we're going to be constructing our circuits in an online program called TinkerCAD, which allows us to simulate our circuits and do our coding in one place. The illustrations I'll be showing in the following slides are from TinkerCAD, but I do want you to keep in mind that these are all real circuit devices. You can get these at like an electronics store, and in college you'll work with these in a lab. These are real circuit elements you can use to build real circuits. We're just doing them online today to make it a little bit easier. So our first guy here is the Arduino microcontroller. At its core, a microcontroller is just a mini computer, one that we can use as a voltage source that we control with code. We can do this through pins, where we connect wires to obtain a certain voltage, just like connecting wires to the terminals of a battery. This allows the Arduino to be the voltage or energy source of our circuit. We have a 5-volt power pin that allows us to connect our circuit to a constant 5 volts. This is exactly the same thing as connecting it to a 5-volt battery. There are also special analog ports that allow the Arduino to measure voltage from a circuit. So these pins are not giving you energy. They're actually a measurement device. And now this is a bit of an advanced topic that we'll be saving for the extension. But it's good to know that the Arduino, one of the other things it can do is actually measure stuff from a circuit and do some useful stuff with that. Lastly, we have our digital pins. And these are the ones that you're going to use in the main lab activity. These function similarly to the 5-volt pin, except that we can use code to switch the voltage on and off, just like opening and closing a switch. We'll see in a little bit that this is actually extremely useful to us. Next up is the breadboard. Breadboards are the platform we will use to connect our circuits together. In the real world, they're used to rapidly prototype circuits because you can just plug wires in or remove them easily, without having to solder anything together. It just makes construction of a circuit very quick and not messy at all. You'll notice that there are these colored columns on the edge. These are power rails which we can connect to the power pins of the Arduino. You may also notice that they're labeled with a plus and a minus, just like the terminals of a battery. The numbered rows then connect across horizontally. That means if you connected a wire into, say, 1A and another into 3A, they would be connected. In a little bit, I'm going to show you a demo of circuit construction in TinkerCAD, so this breadboard stuff will make a little bit more sense. You'll get to visualize it. There's also a workbook activity where you'll get to practice this. So you don't have to memorize right now how exactly a breadboard works, but we do want to introduce you to them. And again, reiterate that these are real things where you can just kind of plug wires in and very quickly create complex circuits without any kind of messy assembly. The star of the show here now is the LED, which is the light emitting diode. These are special cousins of the light bulb that glow only when current flows in the correct direction and when the voltage is large enough. We have two legs of this LED called an anode and a cathode, and current can only flow from the anode to the cathode. If you try to make current flow in the other direction, so basically you take the LED and you flip the direction it's in the circuit, it won't actually work. And I'll show you that in TinkerCAD in a second too. But you can remember that anode to cathode is A to C. So the current only wants to flow in alphabetical direction, which is just a nice way to remember it. You also might realize too that because the LEDs have a certain color, here you see a red one, but they can come in all kinds of other colors as well, that might be really useful to us, right? Because we're constructing a traffic light. So having things that are a specific color, that might be kind of useful to us, just to keep in mind. The other thing too, and this is really important to know, is that LEDs, unlike the light bulb that we saw before, where we were able to change the resistance and it had some notable amount of resistance, LEDs have pretty low resistance. So think about when I set that light bulb to 0 ohms of resistance, that's kind of what an LED looks like to a circuit, or at least very close. This means that if we just hook one up to a battery, there's a very real chance that we could create a short circuit, which would either destroy the battery or the LED or maybe both of them. So what we actually need to do here is to put a resistor in series with the LED to avoid a short circuit. Just like we talked about before, we want to use the resistor to keep our circuit safe. Okay, we're almost there. At this point, we've done our hardware. We have all the components we need to make the traffic light from physical components. The only thing we're missing now to have a true embedded system is software. And this is the final piece of our puzzle, which is how we turn that Arduino from just a voltage source into an actual embedded intelligence. Remember, the final design here is to create a functional traffic light that operates without a human, interacting with it, right? Traffic lights, they're out in the world, they work normally. There isn't someone pressing a button behind the scenes. They work automatically. So we need something that will allow our circuit to operate autonomously. And to do that, we want to be systematic in our approach, right? Because this could get very complicated. So we can make the process of coding quite simple by following a set guideline. First, we identify our objective, which is to make a working traffic light. Okay, we all agree on that. Then we consider our constraints, the rules that are going to govern our system. For example, we know that we need the traffic light to function autonomously, and the traffic light needs to repeat over and over again, right? You cycle red, yellow, green. Well, once I get to green, I need to go back to red, right? We want to keep that cycle going on and on and on. We also want maybe the red light to last this amount of time, the yellow another, the green a third amount of time. So those are some of the rules that we have to follow as software engineers here. Then we develop an outline of what will happen, which is sometimes called pseudocode. This isn't the actual code yet, but we need to think like a computer, and more on that in a second. These first two steps are really important. We call this thinking before you code. And doing this will make you a better coder and save you a lot of time in the long run. Think of it like cooking. You need to buy all your groceries and read the recipe before you actually start cooking anything. Once we've planned out the flow, we finally write our actual code, line by line. We test small parts of our code first to make sure there aren't any errors, which we call bugs. And then we write a little bit more and we test again. And we keep doing this, right? This is a kind of an iterative approach. We call that iterative design because we're using our mistakes to learn and make our final designs better. So like I talked about at the beginning of the presentation, as engineers, we're constantly trying to make small improvements. But instead of just designing the whole thing and then fixing it later, we design little pieces and we fix them immediately. This will save you a ton of time later. And it's a much more efficient way to design anything, but particularly with coding, because there's so many things that can go wrong. Like one error here can cause another error there. So if you make sure that just a couple lines of code at a time work and build up a more complex system, you will be a better coder, especially because, more complex systems get really involved. And if you're debugging something, take it from me, because I have been there. If you're debugging something complex for hours, you'll be really mad at yourself if it's a small issue that you eventually find that you could have saved hours of effort by just fixing it at the beginning of your process. So that's why we're really getting this idea in your heads about checking things a little bit at a time and building your way up. Now back to the idea of pseudocode, and this kind of continues that line of thought. When we think about the logic of the program, we want to think like the computer, going one step at a time. We can write an outline, which takes the form of a flowchart most of the time, where we think through the steps in the decision-making process one by one. This example here shows you the thought process of blinking an LED off over and over and over again. For this lab, if you don't feel comfortable yet with text-based code, you can use block code, which hides the more complicated details in single-step chunks using more human language. You can turn your flowchart into block code pretty easily, and I'll show you how to do that in TinkerCAD. But regardless of whether you choose to use that or actual text-based code, it's important to realize that the computer completes things one step at a time. With code, each line or block in the block code case is a single step. This way, the computer operates the exact same way a chef cooking a recipe does. I'm going to make that analogy again. It finishes one step, and then it does the next, and then it does the next in order each time it runs. Just like you're following a recipe, you don't want to jump ahead. You do each step in order. There's an order for a reason. To complete that analogy, your code is just a recipe for getting the computer to do what you want. Your computer can only do things that you tell it to do. So if you don't include a step, just like if you don't include a step in a recipe, it won't happen. So you have to remember to not leave out any details. The computer won't interpret like what you mean. So using that traffic light as an example, when you sit down to write your code, so you have your circuit wired maybe, and now you're writing the code, you want to go through the steps that the Arduino actually has to take. For example, you need to start somewhere. So maybe you're going to decide we're going to start with the red light. That means the red light has to be turned on, but also you have to turn the yellow and the green light off. If you don't turn them off, the computer won't know, oh, well, you mean to do this. It will leave them on if the green and yellow are already on. So you have to write a line of code saying, turn off green, turn off yellow. Then when it's time to change to yellow, you want to turn yellow on, but you have to remember to turn red off too, right? And then you want to wait, and let the yellow light, glow for a little bit before, okay, I turn yellow off and I turn on green. You have to remember all of those steps. So if you think like the computer, one step at a time, and the computer needing to be told every single step to do, this will save you a lot of time, especially if you write this as a flowchart first before you actually sit down and code. Trust me, it will save you a lot of time. At this point, I'm now going to switch over to TinkerCAD to show you the environment and help you visualize some of what I've been talking about a bit better. Welcome to TinkerCAD. Once you've logged into TinkerCAD using your school email, as shown in the Student Interactive Workbook, you're going to wind up on this landing page. This is the homepage for TinkerCAD, and if you've used this for some of our other labs like 3D printing, this will probably look familiar. You can see down here that if you have any previous designs from the same account, they're saved. So when you're working on this circuit, if you need to close the window and come back later, your circuit will be saved as long as you use the same account. But for this demo, I'm going to start with a brand new circuit, like all of you will. So we're going to go to Create and Circuit. It's going to load for a second, and then it's going to bring up our circuit environment. And it'll have a fun little name that you can use or change to remember it by. So we'll see a couple of things. On the sidebar here, we have the different elements or components that we can instance. We can also use this menu to sort them if we're looking for something specific. We also have a code menu, which we can bring up, which right now, since there's nothing programmable, there's nothing to see, but that will be where our code is done. We'll use this button to start simulation when we want to actually plug our device in. And then we have a few useful utilities like a garbage can to delete elements and some rotational tools. So to start off with, we need an Arduino. So I'm going to take the Arduino Uno R3, click it, and then click again to drop it off. You can also give it a name if you wish. First thing I'm going to do is to rotate it so it looks like the examples in your workbook. So using this little tool here, or the R key, I can rotate it, and now it looks a bit more familiar to us. Let's just look at a couple of the pins to make sure that we're comfortable with what's going on here. So you'll notice here we have 3.3 volts, the V is for volts, and 5 volts, as well as ground. This is the power rails, effectively, that we were talking about before. So we said that we can use the Arduino as a battery, as a 5-volt battery or a 3.3-volt battery. The positive terminal of our battery is this pin. So you can see when I hover over the pin, I see this red square. That means that it's something I can electrically connect to. If I click on it, you'll see now that I'm drawing a wire. And I'll need to click at the other end to connect this wire to something. But this is how I'm going to actually connect things. You can hit the escape key to get rid of it. Ground, remember, is important because it is the negative terminal of your battery. On the right side, we also have the digital pins, which we talked about that we're going to use when we actually code, when we want to flash things on and off. All of these different numbers represent different pins, and they have numbers because in the code, we're going to need to tell the Arduino which pin we're actually using. Next, I want a breadboard. We can just use the small one, click the drop, and again, rotate it, and drag it in a little bit closer so it looks like what we saw before. Now, similarly, if I hover over the different pins, which are these little circles on the breadboard, I see the red square comes up, which again means I can draw a wire. Now also notice that we have other things that are highlighted. So I'm on the positive voltage rail here, or power rail, and you can see that there are these green lines and circles around the whole rail. This means that everything is electrically connected to what I'm currently hovering over. So everything here is the same electrical connection. This power rail is one thing. Then I go over to the negative part of the rail, or ground, and I see that they're all connected, but now not to the positive side. These are two separate terminals. If I go over to the rows then, I notice that they're connected across, but just A through E. They're not connected over to this side, F through J. They're also not connected to the next numbered row down. So these 5 pins are all basically the same place in the circuit, but these 5 are different. If I wanted to connect these two sides together, I would draw a wire across. Now that I have this wire, current can flow into this row, across, and into the other row. If I don't want the wire there, I can delete it with the garbage can. So to do something interesting, let's get some other components out. Let's find an LED. We can drop the LED in, and we'll get this window where I can give it a name, and I can also change the color. So for example, if I wanted a green LED instead, I can do that, and now it's green. This will be quite useful for our traffic light. We also know that we need a resistor, which will allow us to prevent short circuits. So I'm going to pull a resistor out, and this time the window lets us change the actual value of the resistance. This is kilo ohms, which is 1,000 ohms. I can also change it to just regular old ohms, and make it something like, say, 200. You'll also notice the color's changed, symbolizing that it's a different resistance value. So to start off with, I want to connect power. So I'm going to go back to that 5-volt rail, and I want to connect the positive side of my battery. We're going to use the power rail so that we can now connect 5 volts from anywhere along this line. So if I draw another arrow, I now have this row connected to the positive terminal of my battery. I need to make sure I have ground as well, so I'm going to use the ground rail. Now I need to actually instance my circuit elements. So let's start with the LED, because we know the LED is polar, which means we have to plug it in the right way. So we see the cathode and the anode show up. If you remember from before, anode is the positive terminal, and the cathode is the negative. You can remember this because it's in alphabetical order. Things go from A to C, which means that I actually want to rotate this guy a little bit so that I can connect it properly with my battery. So if I plug it in this way, now this first rail, which came from the positive side, goes to my positive leg of the LED, and the negative side is in this row. I also need to use my resistor, which I can just connect this way. And now current will flow through the LED, down through this resistor, into this row 6. Finally, row 6 needs to be connected back to ground to complete the circuit. At this point, I have a complete LED circuit. So if I turn my Arduino on, I should be able to make the LED glow. To do that, I'm going to click Start Simulation. The Arduino plugs in and the LED glows. I have a working circuit. Now, what would happen if I plug the LED in backwards? Remember, current can only flow in one direction. Now it's plugged in the wrong direction. So if I turn the Arduino on, nothing happens. That's because there's no current here. The LED is effectively an open circuit. I also can see now that if I put my LED back together, but perhaps this time I forgot my resistor, and so I instead connected my LED straight to ground. Oops. What would happen? Oh no, we have a short circuit. The LED blew up, for lack of a better term. If I hover over it, I can see, wow, I put too much current through it. So it actually tells you about the absolute current limit, which is effectively a short circuit situation. We drew too much at the Arduino, which can be very dangerous for our electronics in real life. Luckily, as this is a simulator, you have the opportunity to make mistakes in a much safer way. But still, we do want to avoid these, so it's good to know about. Now, the last thing is I actually want to create something that can work with code, something that can blink. So now, instead of using that 5-volt pin, I want to use one of the digital pins that I can control with code. So I'm going to get rid of this wire. And I actually don't need the connection to the positive rail either, because now I want to go straight to the source. So let's just use 13 because it's right here, but you can use any of these from 2 to 13. And let's connect pin 13 right over. We're going to leave the ground connection because this is still a voltage source. We still need to be connected to ground. So we're going to leave that alone. But now we have this pin here, but we need to actually write some code to make it do something interesting. So now if I bring up the code menu, because the Arduino is here, I'll actually see stuff. And you have 3 code options: blocks, blocks plus text, or text. The blocks are just the block code that we talked about. The text is just the text code that we talked about. And then blocks plus text lets you see both at the same time. You can actually create something in block code, and then it will immediately, instantaneously translate it to text code. So if you've never coded before, this is actually a great way to get familiar. The block code allows you kind of to take your pseudocode and just really write it out in a more natural human way. And then that text code is a lot how programmers generally do things professionally. So if you're interested in learning that, this is a great way to learn. But if you've already coded before with text, if you want more of a challenge, you can also go straight to the text code, or you can just use the blocks if the text code is a bit intimidating. These are all valid options. So I'm going to use the block code to simply demonstrate how this works and how we can very quickly get the LED to blink. The first thing that we're going to have to do is we're going to have to start somewhere. So we need the LED to either be on or off at the beginning of our loop. So this thing is called forever. This is our loop. We want the LED to blink continuously rather than just once. So this is what we call a loop, and loops are where things happen over and over and over again until the end of time or whenever you unplug your device. So we're not going to use the built-in LED, so I'm going to get rid of what's actually here. But I want to start by setting that pin to a certain value. So we remember from before that we were using pin number 13. So I'm going to set that pin to either high or low. Remember, high is 5 volts, low is 0 volts. So I'm going to set pin 13 and we'll start high. That seems like a good place to go. Next, I'm going to have to wait until some amount of time to actually be able to see the blinking. If I go straight to just shutting it off, the computer executes code so fast a human wouldn't be able to tell, and it wouldn't look like it's blinking at all. So I'm going to go to control, and I have a wait function. So this block tells me we need to wait for some amount of time, maybe 1 second, because a human can actually see something like that. So I'm going to put that in there. Of course, I could also change the amount of time if I wanted to. Make it 2 seconds, make it 1, but we'll leave it at 1. And now, after 1 second has passed with the LED being on, I need to shut it back off. So go back to output, we're going to use the same block, but this time, we're going to set that pin to low. Oops, actually, that's the wrong one. See, I made a mistake too. This value has numbers in it. This is actually for the analog pins, which we're not using in this example. So it's also a good example to be careful. Some of these blocks do look kind of like each other, so you can make a mistake. But we're actually going to use the correct one. When it says high or low, you know it's a digital pin. And since it's grayed out, you can see it's not going to be executed right now because I put it in the wrong place. See, this block has been turned off. To now attach it, now the code can actually be used. So remember, it's pin 13. That's good, but now we want to turn it off. And remember, low is off. So let me change this to low. And now you might think we're done because, hey, it turns on, we wait, we turn off. But remember that at the end of the loop, it immediately goes back with pretty much no delay to the top here. So if I actually want to have the blinking work properly, I need another delay because I need to delay on both sides of like the on-off routine. So I'm going to put another wait in. We're going to make it the same amount of time so it's nice and consistent. And now we should have a proper loop. If you've been paying attention along, you may also notice that this has been updating all along, and there's some nice comments here so you can see what's going on. But now what I'm going to do is I'm going to start my simulation, and if I did this correctly, everything should start blinking. So it starts up, and there we go. The LED is blinking, 1 second on, 1 second off, over and over again. And until I stop the simulation, it will keep doing this because it's in that loop function. This is like the basic kind of coding example to start off with when you're working with an Arduino. So at this point, I hope that you have a bit more of an idea of how to work with TinkerCAD. You can come back to this recording as you're working if you're confused. And the Student Interactive Workbook also walks you through this in a bit more detail. So if this felt a little overwhelming, don't worry, you don't have to memorize it all right now. But now that we're finished with TinkerCAD, I'm going to return to the main presentation and give you all the rest of the details about your traffic light project, and then we can begin to wrap up. Welcome back. As I've hinted at, we want you to take the sample circuits and effectively build them up to create a circuit with 3 LEDs of the appropriate color that act as a traffic light. Specifically, we want a red light that lasts for 3 seconds, a yellow light that lasts for 1 second, and a green light that lasts for another 3 seconds. Then we want to loop back and have this traffic light just kind of keep working on and on. Using the example code from the coding problems, as well as what I just showed you in TinkerCAD, you should know now how to create a loop, and you'll have all the other building blocks that you need to create code that does this. Completing this circuit will then show that you have a mastery of all the skills in the practice problems. You'll know how to use hardware, you'll know how to use software, and you'll be an embedded systems expert. This now brings us to the conclusion of our main presentation. You're now ready to go off and start working in TinkerCAD. We talked about a lot of topics today, so if any of them resonated with you and you'd like to learn more, there's a small sampling here of the topics that you or your teacher may want to research. But I remind you that this is only a subset of a very, very big field. We talked at the beginning about how all of these ongoing problems will be, solved by embedded systems, or at least in part. But this is just a kind of a place to start. The Internet of Things, too, in particular, is a big topic these days. And it's essentially what happens if you put Wi-Fi or Bluetooth in these individual embedded systems and have them start talking to each other. So if you've heard of like smart TVs, smart fridges, you have those in your house, those are examples of the Internet of Things. And that's like a network of embedded systems all working together. And one last time, engineering is interdisciplinary. It's a team sport. I can't stress that enough. These are just some of the majors and fields that are relevant if this topic really spoke to you. But remember, again, many engineers nowadays are working with embedded systems. Again, these are just the people who really have the particular background in software and coding and circuits. I'm now going to continue with a discussion of the extension activities for this lab. So if you're interested in exploring these activities, please keep watching, or feel free to come back to this section after your traffic lights are complete. Otherwise, I wish you all good luck with your builds, and thank you again for joining Engineering Tomorrow. We look forward to seeing you in our live sessions. At this point, we'll be diving deeper into the concept of embedded systems, as well as introducing some additional circuit elements you can use at TinkerCAD, like we saw in that drop-down menu. The objective here is to expose you to different concepts rather than assigning a specific project. So we're not building towards something like the traffic light. Instead, this is a bit less structured, and we're just kind of, giving you a taste of what else is out there. So feel free to come back to this section as is needed, or to just watch this, several parts at a time. Your workbook also will go into further detail and give you practice with these individual topics. Now, another way to understand embedded systems is through the concept of sensors and actuators. Sensors react to changes in the physical environment and produce an electrical signal, usually a voltage. that our embedded intelligence can read and interpret. Actuators perform an action, usually a physical action, in response to current and voltage in the circuit, such as emitting light or heating up or moving. Now that you have the definition, let's do a quick activity. Which of the objects pictured here is a sensor or actuator? Can you guess? An LED, which we saw earlier, is an actuator because it emits light because current's traveling through it. That's pretty straightforward. The switch, on the other hand, is a sensor because it detects whether it's opened or closed, which means it's detecting position. The fan is an actuator because it spins to move air, right? That's a physical action. And the solar panel can be thought of like a sensor too, because it creates a voltage when light shines on it. Another way to think of sensors and actuators is in terms of input and output. Sensors provide electrical input to your system, while actuators serve as the output, the thing you're using your Arduino to control, like a fan or a light bulb or a speaker. One way to adjust settings like brightness, volume, or temperature are knobs. Knobs are actually a type of sensor called a potentiometer. A potentiometer, at its most basic, is just an adjustable resistor. You're turning the knob to change the resistance between some maximum and minimum value. Now, how does that work? Well, in reality, a potentiometer is actually a 3-terminal resistor, as you can see in this diagram, where we effectively have 2 resistors, one between terminal 1 and the output, and the other between terminal 2 and the output. By turning the knob, we move this thing called the wiper across the resistive material. Now, imagine the wiper being at different points. The distance from either terminal to the output will be different. So if you measured the resistance on each path, it would also be different. A good way to use this in a circuit could be to connect the output terminal to ground and then either terminal 1 or 2 to the rest of your circuit, say an LED. Now your circuit consists of a voltage source and an LED and a variable resistor. So remember how we saw that changing the value of a resistor, in the light bulb changed, the amount of current and how bright the light bulb was. And you can imagine that changing the resistor in an LED circuit does the same thing. Now, you're able to constantly just tune the resistor, by changing a knob. How might that be useful? What kind of circuit have you now created? The rest of the potentiometer can also just be thought of as a ratio of resistances, because you actually, as I said, have 2 different resistances there. So by tuning that wiper, and you might get a sense of this just from that picture, you're creating a ratio between the terminal 1 to output resistance and the terminal 2 to output resistance. So if you connected those LED circuits on either side to 2 different LEDs to the 2 different terminals, you should actually be able to tune something where one LED gets dimmer and the other gets brighter because you're adjusting this ratio. So there are a couple of different ways you can use potentiometer. You could just use it as a variable resistor, but you can also use it to create these ratios. And there's interesting things that you might think about using that to do as well. There's also a lot of other sensors, both in the real world and in TinkerCAD. Again, you saw that drop-down menu. One way we can classify them is as being either analog or digital. So a digital sensor sends either an on voltage or an off voltage. When we use the digital pins for the traffic light, we're sending digital signals. High equals 5 volts equals on, and low equals 0 volts equals off. This digital world is how computers think, ones and zeros, what you may have heard of as binary. Digital sensors can represent an event with only fixed outcomes, what we sometimes call binary state. The best examples of these types of sensors are switches, which are either pressed, which is on, or off, which is not pressed. On the other hand, an analog sensor can output voltage levels that vary across a continuous range. To say something is analog means that there's a continuous series of numbers we can use to represent it, rather than a simple on or off. The world we live in is analog, for example. If we lived in a digital world, we'd only be able to go outside and say, today is cold or today is hot. There wouldn't be any in between or nuance. But because we live in an analog world, we can actually measure things with real values, right? We could say, oh, today is 55.4 degrees Fahrenheit. And you have decimal points for greater accuracy and stuff like that. There's a continuous range. we can quantify things, using that continuous range of numbers, right? So some examples of an analog sensor are the potentiometer, where we're just turning this knob, and as we turn the knob, we're getting different resistance values, and therefore continuous series of resistance values leads to a continuous, series of current values that we can select in our circuit just by tuning that knob. As well as a temperature sensor, which can output, real numbers, a continuous series of numbers that represent temperature, right? The temperature sensor doesn't just say hot or cold, it tells you, 55 degrees, that kind of thing. So, if that was a little unclear, to summarize, really the key takeaway between analog and digital here is that if something has a fixed set of states, it's digital. If there's a continuous range of values to move between, it's analog. If you've ever seen one of those fans that have like a fixed knob where you turn it between like off, low, medium, high, and it's like just those 4 settings, that's actually a digital switch, because even though there's more than 2 settings, you're switching between fixed states. There's no in between. It's either low, medium, or high. There's no other, alternative ideas, right? Like that is what it is. But if you have like an old radio where there's like a real knob that you can tune, and like you can use the knob, either the tuning knob or the volume knob, both of them are analog. That's analog because it's just a continuous range. You can adjust that volume until it's exactly where you want it to be. You can tune for the radio station. It's not like, oh, I just select the radio station. You can kind of tune and the radio station gets a little bit in or out of tune, right? There's a continuousness there. And that is really what analog is. So you'll see in TinkerCAD that sensors come in all shapes and sizes and degrees of complexity. Some are simple, sure, only being 2-terminal devices like the switch. We saw that. That's basically the most simple sensor you can get. But others are quite complex. They have multiple terminals, and the real devices have their own internal circuits. They're doing a lot of thinking inside, right? There's stuff hidden under the hood, if you will. Many of these more complex sensors have 3 terminals or even 4, with 2 of them being a positive and a ground, because it needs to have power, especially since it has its own circuit inside. And the third is the signal terminal. This is where you connect to your Arduino to actually measure something, right? Depending on whether the sensor is digital or analog, you'll connect it to either a digital or analog pin. So all of them, although they work differently on the inside, they generally follow, the same idea in that they use some kind of physical phenomenon that creates voltage or current from outside stimulus. In reality, there are a number of ways to create voltages, and sometimes currents, but particularly voltages, using different physical phenomena. One example is a microphone called a piezoelectric microphone, where you're able to convert mechanical vibrations in a crystal lattice to a voltage. So sound creates a electrical voltage signal that you can then read on a computer, and that's how you digitize sound. Another example could be, again, we talked about, the solar cell, and there's something called a photo detector, which detects whether there's light or not and how intense the light is. That uses optical energy to create electrical current in a circuit. And so those are just a couple of examples. Now that we've discussed sensors, there are also actuators we can find in TinkerCAD as well. And those are perhaps even more fun because we actually get to do stuff that we can see with them, right? And by the way, of course, we saw that drop-down menu, but if you want to find the full list of sensors and actuators, you can go to Components and select All, and TinkerCAD lists input for sensors and actuators as output. So if you're looking, it doesn't call them sensors and actuators, it calls them input and output. So we have regular light bulbs. We talked about these before. Again, remember that they're not like LEDs in the sense that they actually have resistance. They're just big resistors. But they're like LEDs in the sense that changing the amount of current and voltage will change how bright they are. But since they have their own resistance, we don't need to put an extra resistor in series. And we don't care about the direction. There's also a cool type of LED called the RGB LED. That is a special LED that has 3 inputs made up of a red, a blue, and a green LED all rolled into one package. We can use this to create any color of light we want. And in your workbook, there's a section all about how mixing these 3 colors creates all the other ones. I think that's really cool. So that might be something you want to check out. There's also the piezoelectric buzzer. So I just mentioned how microphone works. This is the other way around. This takes in an input voltage and causes the speaker to vibrate, which outputs sound. So now it's an actuator instead of a sensor. So some devices can work both ways. Depending on how you hook them up, they could be a sensor or an actuator. So you can use that to create sound, and TinkerCAD does allow you to make sounds. Maybe you want to try to create a musical note using just code. And lastly, we have the multimeter, and this is the most essential piece of electrical engineering lab equipment. So if you decide to major in electrical engineering, computer engineering, when you take your first labs in college, you will become very, very familiar with this guy, or maybe you're even doing this in high school. These guys allow us to measure voltage, current, or resistance. So if you want to actually quantify what's going on in your circuit, this is how you do it. And so maybe you want to use this just to debug your circuits too. That's something else to keep in mind. Once you combine sensors, actuators, and codes, you can get some fully fledged embedded systems. We did the traffic light, so you've already built an embedded system, but we can get some really, really complex things that do some really cool things. So this example here allows us to control the speed of a motor using a potentiometer as a knob. And that's really cool, but maybe you want to do it entirely with code. There's a lot of ways you can just take an existing project and modify it in some way to improve it. Again, iterative design. I'm going to say that again. And that can also be a way if you're looking for something to do. You're trying to be creative. That's another direction to approach. You don't have to create something from scratch. You can also iterate on an existing design. And worth knowing too, right? Some sensors will interact with code in different ways. So some of them you're going to read the sensor value and write it straight to an output. Some of them you may have to do something with the code. You read the value, you save it as a variable, and then you have to do something to it, mathematically before you can output it. Kind of play around with that, look at our examples. And, if you want to even look some of this stuff up on the internet to really just go even further, again, feel free to do so. This is very much a learning experience for you guys, but we want it to be kind of an open experimentation kind of environment as well. At this point, you're ready to dive fully in. We've shared some more information with you. But again, if you haven't found them yet, these slides are at the end of your student interactive workbook in the extension section. They'll introduce you in more detail. They'll give you some practice. They'll get you comfortable and build your confidence, which is really what we want to do. But again, I want to encourage you to be creative. Go beyond what's in the workbook. Again, they're not physical circuits, so feel free to work fast and break things. You learn from your mistakes. And since your mistakes aren't physically breaking anything, this is the best way to prototype. Without there being any kind of physical risk. So really just try different things and be creative as possible. The possibilities are really endless. That's really not hyperbole. That's true. But at this point, this is the conclusion of our embedded systems presentation. Again, I hope you have fun with your builds. Thank you again for joining Engineering Tomorrow. We're looking forward to seeing you in our live sessions, and we can't wait to see what your creativity has brought.